Good morning, Sandeep Sharma. I'm the manager of operations planning in ERCOT. I've been in ERCOT for almost 14 years, and my responsibilities are primarily focused in the area of renewable integration, ancillary services, and frequency control. Today, I am here to talk to you all about ERCOT's experience with integrating renewables, as well as also highlight some of the key features of our market design that helps us manage higher penetration of renewables. The outline of my presentation today includes providing a high-level background information of ERCOT, and then briefly talk about renewable integration practices and solution at ERCOT, and then also key elements of market design, ERCOT market design. I'm going to highlight those key features of our market design. So what is ERCOT? ERCOT is a non-profit independent system operator. Uh, Created in 1999 when Texas legislature restructured the Texas electric market and assigned ERCOT with four primary responsibilities: system reliability, competitive wholesale market, open access to transmission, and competitive retail market. And like I said, we are non-profit and regulated by Public Utility Commission of Texas with oversight from Texas legislature. We do not, we're not a market participant, and we do not own any generation or transmission wires. This slide number 4, provides us with a brief summary of our records. ERCOT, in its peak, it's roughly 75 gigawatt grid. Our weekend peak demand is roughly 72 gigawatts. Our winter peak demand is roughly 66 gigawatts. And our instantaneous wind record is actually 21,144 megawatts is our instantaneous, which was made about a month and a half ago, May 7th at 8:43 p.m. Our penetration record is roughly 59.30%, which was made at 2:10 a.m. on May 2nd, when 59.3% of load was being served by wind, and total megawatts served by wind when we made the penetration record was 19,426 megawatts was coming from wind. There are other records, but I'll let you read those. And so if you look at if you look at our renewable integration experience, the best way to tell our story is using the construct of these five different pillars that I consider are instrumental in our our success in renewable integration. And so the first pillar being grid code, the second being renewable forecast, ancillary service being the third, and then risk assessment and real-time operations. And what we will realize is what we have experienced is each of these pillars play a key role in overall efficient and reliable integration of renewable uh, renewable resources into the grid. Starting with grid code is one of the most important thing to pay attention to, and having the right grid code early on ensures that problem will not happen in real time, or if there is a problem, that problem will be mitigated as expected in real time. The good thing with having a clear cut grid code requirements is if you have to solve the same problem in real time, it's fairly more expensive, and and ends up actually making the renewable integration more expensive. And so having clear cut grid code requirements early on uh, helps operate real time more efficiently and more reliably. And then the second pillar, renewable forecast. ERCOT today, in the context of both wind and solar, we have both wind and solar forecast. Wind and solar forecast is, one of the key component of key pieces of integrating renewables. The challenge with renewables is renewables are variable and uncertain, and forecasting provides some certainty uh, to the variable and uncertain renewable energy. And today we have two different vendors providing two different kind of forecast. For wind, for solar, we have roughly about 3000 megawatts of installed capacity. That's why we only have one solar forecast. And then we have intra-hour wind forecast. And without forecasting, there is no way we would have been able to efficiently and reliably integrate almost 25 gigawatts of wind and 3000 megawatts of solar energy into our grid. And based on what the forecast is expected, we plan other resources and we commit other resources around what the wind and solar resources are expected to do. And so the third pillar, if you look at the forecasting, will never be right. And so there's always an uncertainty associated with forecasting. There's always a risk that the forecast will be wrong, and it will be wrong. And how do you address that risk associated with the risk associated with uncertainty built into the forecast? And ancillary service is one of the tools that we use to mitigate our risk associated with variability and forecast uncertainty. ERCOT has roughly four different categories of ancillary services, starting with regulation up and down service, responsive reserve. The regulation up and down service is primarily targeted towards solving seconds to second variability in the grid. And it's a 5-minute product. The responsive reserve service is based on primary frequency response capability. It is, and then a portion of responsive reserve is also provided by demand respond that can respond within 30 cycles of frequency hitting the trigger limit, which is for ERCOT set at 59.70 hertz. Our under frequency load set is actually set at 59.30 hertz. So we're trying to protect under frequency load shed for a loss of two nuclear units with responsive reserve. And the other components of responsive reserve that we recently added is called fast frequency response. It responds at a frequency trigger limit of 59.85 hertz, and full response is provided within 15 cycles, and actually helps us with some inertia. The speed of the response actually helps mitigate inertia concern to some extent, not fully, but it does mitigate the inertia issues. And then the fourth pillar is risk assessment, and the primary reason for the fourth pillar and the risk assessment is associated with the fact that our ancillary services are predetermined numbers, and they are determined uh, you know by the end of this year we would determine the ancillary service requirement for next year. And so there is some risk built into that and some uncertainty built into that. So risk assessment that is done anywhere from 6 hours to 8 hours before the real time helps us ensure that ancillary service that we have procured are sufficient to address any reliability issue in real time. And then when we come to real time, that's when the rubber meets the road. And so everything that you planned for with grid codes, with forecasting, with ancillary service and risk assessment is tested in real time. And in ERCOT market, wind and solar pretty much can generate, and they don't have to follow a base point, uh, as long as system reliability is not at stake. But if there is a transmission constraint or a reliability is at stake because of a stability issue, then they have to follow the ERCOT dispatch instruction and generate at or below the dispatch instruction from ERCOT. And they do provide frequency response in real time. So with that, the next slide, I'm going to briefly talk about, a and give you a high level overview of our market. And so ERCOT has a day ahead market, and the day ahead market is primarily willing buyers and willing sellers. And also in the day ahead market, we procure ancillary services. And so right after the day-ahead market is executed, we run day-ahead reliability unit commitment. The reliability unit commitment is really where we are looking at next day, tomorrow, and trying to assess whether or not the amount of commitment that market participants are making will be sufficient to meet the system demand and ancillary services. And generally, most of the time, the market committed resources are sufficient, but there are few instances when it's not sufficient. And if it's not sufficient, then ERCOT can do a reliability commitment. Most of the time we don't do reliability commitment because market participants, we wait for closer to real time, depending on startup of units and startup time of the unit. But we wait closer to real times and give opportunity for market participants to self commit. And then after the DRUC, there's the hourly RUC mechanism. And I think this is one of the important feature of our market, which is happens in adjustment period, which is defined as period before operating period. And what's happening with the hourly reliability unit commitment is basically we are looking at the wind forecast and solar forecast, which is part of the wind and solar unit COP, current operating plan. And then we are looking at all the other commitments of the unit, and we're trying to figure out based on the forecast, based on the latest forecast from wind and solar, whether or not there is, and whether or not there is sufficient margin available to meet the ancillary service requirement and still meet the system demand. And so that check is done every hour for the remaining day, and it's done in adjustment period. And then the operating period is really characterized by two things, which is hour ahead and operating hour. And during the operating hour, it's actually the real time, and we have a security constraint economic dispatch that is dispatching resources based on the offers. And it's also looking at transmission constraints. It's doing both economic dispatch and security, and looking at the system security and dispatching resources accordingly. And it runs every 5 minutes, and it's only looking out next 5 minutes. And like I mentioned previously, both wind and solar resources are dispatched, at their current output, and they are not required. They can move around and not have to strictly follow the ERCOT dispatch instruction unless they receive a curtailment instruction from ERCOT. And generally, the curtailment instruction would be as a result of transmission constraint or excess energy. And then deviation from there's a penalty for deviating from their base point, and that deviation penalty is applied only when they receive a curtailment from ERCOT. And there's a figure that shows how a resource, the blue trace is that megawatt output, and then the purple trace is the high limit of the unit, and then the dark blue is the base point that ERCOT dispatches every 5 minutes. And what you'll see is pretty much before 110, in the white area where it's not shaded gray, they are pretty much doing what they can do based on the wind speed or irradiance in case of solar. But once they receive a curtailment flag, which is the gray area, then they are dispatched down to zero output, and then they do follow and reach the zero output. And then right after 115, they are released from curtailment, and they again go back and follow the base point. So it works pretty well. The next, and the previous slide is one of the key feature of our 5 minute SCAD dispatch in 5 minute real-time market where wind also gets dispatched, and they have to follow the dispatch instructions anytime there's a reliability issue. The next thing that I wanted to talk to you about is the next slide is really about power balance penalty curve. And what that means is if there is a lot of variability or shortage of flexibility in real time, our market design has a feature which will price the scarcity in flexibility at a very high price. And so the power balance penalty curve, or also called SCAD under-generation power balance penalty curve, it defines the price for any shortage in ramping capability. So roughly a 200 megawatts of shortage of flexible ramping capacity can raise the price to be as high as $9,000. And so the combination of scarcity pricing and power balance penalty curve creates an opportunity for resources that can respond really fast and are flexible. And so what we have seen is, as we have added more wind and solar, we have also seen a pretty robust growth of resources that can, thermal resources like gas units that can start quickly and respond to any ramping needs or any variability, uh, you know, any ramping needs or any flexibility needs because of wind ramping down or solar ramping down. And so those resources have been consistently added into our grid together with wind and solar. So as we added, this slide goes up to 2019, but by the end of 2019 we had almost 25,000 megawatts of wind and solar install capacity. And if you do look at the install capacity of the gas unit, what you will see is, at the same time, we also added more than roughly 6,000 megawatts of gas units that can quickly start in less than 1 hour and fully ramp up in less than an hour. Now, there are a lot of gas units, roughly 4,000 megawatts, which exist in our fleet that are quick start capable, which means they can start, sync, and then ramp to their full capability in 10 minutes. So that provides us with a lot of flexibility, and the market design actually supports that. So this slide, you know, really summarizes some of the things that I've previously discussed. The first bullet point being, the importance of redispatching every 5 minutes. The more granular your dispatch intervals, the less, the lower the magnitude of variability or uncertainty you have to manage. And so by dispatching every 5 minutes, we reduce the uncertainty associated with wind and solar. And also our skate base points, we run every 5 minutes and they are effective immediately. And I know of number of ISOs that run the 5 minute market, but then the base points are effective, 10 minutes after or 15 minutes after. And so a lot of things can happen with wind and solar in 10 minutes and 15 minutes, more so with solar because solar is more variable over a smaller time span compared to wind. And then the third feature of our market design, which is power balance penalty curve, it incentivizes flexibility. with high penalty price for lack of ramping capability. And the other thing that we do is where with the edge truck that I previously mentioned, we are continuously every hour our reliability unit commitment algorithm is application is running, and that application is looking at the latest forecast for wind and solar, and it's looking at the latest unit commitments and trying to assess, whether or not the latest for load forecast that is in the system can be met using the all the unit commitments, uh, decisions that we have received, and wind and solar forecast that we have received. And what that does is, as your system continuously is changing with wind and solar, your risk assessment is also continuously up to date, so you're not behind. And then the fourth point is, the important thing in our market design is that, wind, we dispatch wind every 5 minutes. If there is no transmission security issues, then we are pretty much allowing wind to generate and not follow the base point and pretty much generate based on wind speed or irradiance in case of solar. But if there is a transmission issue, then they are required to generate at or below our instruction. And then the last point is, it's really about what we are working on future. We're currently working on enhancing our market design, so that we can co-optimize ancillary service with energy in real time. Today, we procure ancillary service in our day-ahead market, and in real time, QSCs are required to provide that. But with this enhancement, we will be co-optimizing ancillary service and re-clearing ancillary service every 5 minutes in real time. So that was the last slide. Thank you uh, for listening to this presentation. If you have any questions or comments, my email address is noted down here, and you can reach out to me. Thank you, and all the best.